Good morning. We will see the remaining part of the derivation for laminar flow through two parallel plates. Ratio of maximum velocity to average velocity, drop of pressure and shear stress distribution. The ratio of maximum velocity to average velocity will be our first derivation. In the last lecture, we saw the velocity distribution. From that derivation, we got the formula u is equal to minus 1 by 2 mu dou p by dou x into bracket ty minus y square. Here, t is the distance between two parallel plates and y is the distance at which we are calculating the velocity. At the center, that is when y is equal to t by 2, velocity will be maximum. Replacing y by t by 2, we will get u max is equal to minus 1 by 2 mu dou p by dou x into bracket t multiplied by t by 2 minus t by 2 bracket square. So making the simplification, we will get u max is equal to minus 1 by 8 mu dou p by dou x into t square. This is our first equation. Next is to calculate the average velocity, and it can be calculated by obtaining Q by A. Q is the average discharge flowing through cross section area A. These are two parallel plates which has a distance t in between them and through which discharge Q is. Inside the board, the thickness of the plate is assumed as a 1. So cross section area is nothing but t multiplied by 1. To find the discharge, we will consider one small strip which has thickness dy. Now we have to calculate the discharge through that small strip which has thickness dy. dq is the small discharge through that small strip. It can be calculated by multiplying the velocity and area. That is, q is equal to area into velocity. So dq is equal to minus 1 by 2 mu dou p by dou x into bracket ty minus y square. This equation is nothing but velocity at distance y multiplied by area of cross section dy into 1. After integrating in between the limits of 0 to t, we will get integration 0 to t minus 1 by 2 mu dou p by dou x, which is a constant part, and we are integrating with respect to dy. So integration of y and integration of y square. So taking the integration, q is equal to minus 1 by 2 mu dou p by dou x into bracket integration of y is y square by 2, and similarly we will get y cube by 3 as a result in between 0 to t. So putting the limits, we will get this equation t cube by 2 minus t cube by 3. Making cross multiplication, we will get minus 1 by 2 mu dou p by dou x t cube by 6, which is equal to minus 1 by 12 mu dou p by dou x into t square. Finally, u bar is equal to q by a. We have here the equation of average discharge, that is minus 1 by 12 mu dou p by dou x into t square divided by t into 1 is the cross section area. So we will get minus 1 by 12 mu dou p by dou x into t square as a average velocity. So u max by u, you will get, taking the ratio, minus 1 by 8 mu dou p by dou x into t square minus 1 by 12 mu dou p by dou x into t square. So cancelling dou p by dou x, t square by t square, mu with mu, you will get 3 by 2 as a ratio. And this is the final equation, u max by u bar is equal to 3 by 2. In previous derivation of u max by u bar for circular pipe, the answer was 2, and here we are getting 3 by 2. Let's move for the next point, that is drop of pressure head for given length L. Suppose there are two parallel plates. We are considering two cross sections, section 1 and section 2. Both the sections are separated from each other by distance L. First section is at distance x1, second section is at distance x2 from initial position. P1 is the pressure at section 1, P2 is the pressure at section 2. We will consider horizontal distance as x and vertical distance as y. We have the equation of average velocity. U bar is equal to minus 1 by 12 mu dou p by dou x into t square. We have to rearrange the terms by taking dou p by dou x on one side and other terms on other side. Then in next step we will make the integration of both the sides. Integration in between limits of 2 to 1 dp is equal to integration between 2 to 1 minus 12 mu u by t square into dx. This term minus 12 mu u bar by t square is the constant term. Only dx is the variable. So in between the limits we will get p1 minus p2 is equal to minus 12 mu u bar by t square x1 minus x2. After making the sign change, 12 mu u bar by t square into bracket x2 minus x1. But x2 minus x1 is nothing but L. Here you can see x2 minus x1 is nothing but L. That is length. Replacing that, P1 minus P2 will be equal to 12 mu u bar L by t square. This is the pressure difference in between the length L. Next, we will calculate the pressure head loss. For that, we will divide both sides of equation by rho g. P1 minus P2 by rho g is nothing but pressure head loss, which will be equal to 12 mu u bar L divided by rho g into t square, and this is the final equation. Lastly, we will find shear stress distribution. For that we will use Newton's law of viscosity, that is tau is equal to mu du by dy. Here this u we will replace by our formula of u. Replacing it, we will get this equation. Tau is equal to mu dou by dou y of this equation is of u. We have to take the derivative of this with respect to y. So derivative of y will be 1 and derivative of y square will be 2y. Taking this step, lastly we will observe that mu is getting cancelled with mu. So finally tau is equal to minus 1 by 2 dou p by dou x into bracket t minus 2y. In this equation, minus 1 by 2 dou p by dou x and t are constant. So we can say that tau is varying with y linearly. This we have discussed. Tau will maximum when y is equal to 0 or y is equal to t, that is at the walls of plate. Tau will be 0 when y is equal to t by 2 at the center. Here when y is equal to t by 2, t minus t will be there and equation will be 0. Maximum shear stress can be calculated by putting the values as we have discussed before. So this is the equation tau 0 is equal to minus 1 by 2 dou p by dou x into t, and that will be the final equation. Thus we have completed the derivation part of the laminar flow through two parallel plates. Thank you.